Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 8 on linear and quadratic systems. Now you looked at systems of equations pretty extensively in Algebra 1 and a little bit even in geometry. So let's jump right into it and review even what a system of equations is. Alright, a line and a parabola. Now a system of equations is comprised of two or more equations with two or more variables. One type of system occurs when one of the equations is linear, i.e. when you graph it, it's a line, and one of the systems is quadratic, which in this course means it could be either a parabola or it could be a circle. To solve a system of equations means finding all points of intersection of the two relationships. So let's jump right in exercise number 1 and take a look at a parabola and a line. Exercise number 1. Consider the system of equations shown below consisting of a parabola and a line. Y equals 3x squared minus 8x plus 5, and y equals 4x plus 5. Letter A, find the intersection points of these curves algebraically. Emphasis on the word algebraically. All right, so we want to find out where this line crosses that parabola. Now, because of that, our first step is always going to be basically to set the two equations equal. Because by setting 3x squared minus 8x plus 5 equal to 4x plus 5, what we are literally doing is asking the algebra to find all the values of x where this y value is equal to this y value. So let's start with that step. Here we go. We're going to have 3x squared minus 8x plus 5 equal to 4x plus 5. Now, to solve an equation that has an x squared in it, we basically have two choices at this point. We've got completing the square, and we've got the zero product law. And throughout, we're going to be kind of what I would call biased towards the zero product law, primarily because completing the square works really well as long as the coefficient on the x squared is equal to 1. Here we have a coefficient of 3, not so nice. Now, in order to use the zero product law, obviously we have to get the entire equation equal to 0, then factor both sides of it, or factor the side of it that's not equal to 0, kind of hard to factor the side that is equal to 0, and then solve using that. I'd like you to pause the video right now and see if you can work through this and find the values of x that solve this equation. All right, let's do it. Well, the first thing we want to do is get the equation equal to 0. To do that, I'm going to subtract a 4x and a 5 from both sides of the equation. So here we go. Minus 4x minus 5, minus 4x minus 5. That's going to give me 3x squared, got to be careful here, minus 12x. 5 minus 5 is 0, so nothing there. And then this side of the equation is equal to 0. Once we have the equation equal to 0, we want to factor the non-zero side. Keep in mind, of course, we have four types of factoring. GCF, the difference of perfect squares, simple trinomial factoring, and more complicated trinomial factoring that includes factoring by grouping. This is a binomial, so obviously the two trinomial types of factoring are out, which means it's either a GCF or the difference of perfect squares. But 3 is not a perfect square, 12 is not a perfect square, x to the first isn't a perfect square. This is just GCF factoring. And in fact, right, we see that each one of these two numbers is divisible by 3, and since this has an x squared and this has an x to the first, we can factor out a 3x. That's going to leave me with an x minus 4 inside of the parentheses. Once we have our equation factored like this, now the zero product law really kicks in. And we can kind of group that 3 and x together. And we can say, well, either 3x is equal to 0 or x minus 4 is equal to 0. So either 3x is equal to 0 or x minus 4 is equal to 0. In this case, of course, we can divide by 3 on both sides. 0 divided by 3 is 0. Please don't leave it as 0 over 3. That's just kind of weird. I don't even know what that means. I guess it would mean 0 thirds, which would be 0. If you don't have any thirds, then you don't have anything. So here we go. We have x equals 0 and x equals 4. And what that algebra is telling us is that this parabola and this line cross each other at an x value of 0 and an x value of 4. But solving a system means finding the values of both variables, both the y and the x. So we've got the x values. Now we could take either one of these and substitute them into this equation or this equation, and it really doesn't matter. And given that you have a calculator with the store feature and all of that, it's probably equally easy either way. For now, because I don't want to quite break out the calculator yet, I'm going to just throw them into this equation. So here I'll have y equals 4 times 0 plus 5. 4 times 0 is 0, plus 5 is 5. So that means one of my intersection points is 0, 5. Then here, if I throw the 4 in, I'll have 4 times 4 plus 5, which is 16 plus 5, and that's 21. So my other intersection point is at 4, 21. Maybe make that look a little more like a 21. Excellent, right? Our algebra, solve it algebraically, has resulted in these two coordinate points. And now let's verify it using our graphing calculator. Let's take a look at letter B. Using your calculator, sketch a graph of this system on the axes to the right. Be sure to label the curves with equations and intersection points. Awesome. So what I'd like you to do is break out your graphing calculator, slap this in F1, this one in F2, set your window so that it's got the same window size as what I've got here, and go ahead and sketch that graph. Awesome. Well, of course, I've got the magic board that's already kind of doing it for me. Here I've got my parabola in blue, my linear equation in red. I've labeled both of them with their equations. The only thing I need to still do is put their intersection points up. Here's that one at 0, 5. Here's the one at 4, 21. And again, the beautiful things about modern graphing calculators is that we can now very quickly check to make sure those intersection points are correct. So let's do that. I've already put the graph on our calculator. I've adjusted the window so that it's the same size as what we had before. Let me bring this a little bit more to the window. And let's just refresh how to use the intersect command. I know that we've used it quite a bit already in the course, but I just go into my menu. I go down to Analyze Graph, and choice 4 is my intersection. On the TI Inspire, I'm going to just drag this vertical line to the left of one of the intersection points, hit Enter, drag it to the right, hit Enter, and I've got that intersection at 0, 5. Let's do it again. Go into Analyze Graph, go to Intersection, drag it to the left of the intersection point, that's lower bound. Drag it to the right of the intersection point, hit Enter, that's upper bound. And there's our other intersection point, 4, 21. And it's really rather lovely. In fact, if they said solve the system, but they didn't say to solve it algebraically, we could certainly just solve it graphically. We'd have to draw a well-labeled graph. We'd have to put the equations of both of the two functions on there. We'd want to show our intersection points, and then we'd also want to show our graphing window, and we would have our answers. But this one specifically said solve it algebraically, and so we want to do it algebraically. All right. Let's see if you can do one of these on your own. Exercise number 2. Algebraically solve the system of equations shown. Y equals 8x minus 3 and y equals x squared plus 4x minus 15. All right, so I'd like you to pause the video, start by setting the two equations equal, and work all the way through it to try to find the intersection points of that line and that parabola. All right, let's do it. So step 1, set the equations equal. X squared plus 4x minus 15. I always kind of like having the sort of larger or more complex one on the left. Not 8x minus 5. How about 8x minus 3? All right, I need to get the entire equation equal to 0. That's going to force me to subtract an 8x and add a 3 to both sides. When I do that, nothing combines with the x squared. The 4x minus 8x gives me negative 4x, and negative 15 plus 3 gives me negative 12 equals 0. Right? I'm looking for two numbers that have a product of negative 12 and a sum equal to negative 4. Those two numbers ends up being 2 and negative 6. So I can now factor my trinomial as x plus 2 times x minus 6 equals 0. I can now take x plus 2 and set it equal to 0, and x minus 6 and set it equal to 0. That's going to give me x equals negative 2 and x equals positive 6. There are my two x values. Now remember, I can substitute them into either one of these two equations, but if I'm going to do it by hand, the linear tends to be the easier one. So I've got let me just write that equation here so that you've got it. Right, I'll substitute them into this equation. I'll have y equals 8 times negative 2 minus 3. That's negative 16 minus 3, so negative 19. In this situation, I'll have y equals 8 times 6 minus 3. 8 times 6 is 48, minus 3 is 45. And therefore, my two intersection points are negative 2, comma, negative 19, and positive 6, comma, 45. Right? The two locations where my parabola and my line cross. Very straightforward, right? In fact, you should have been doing problems even like this as early as Algebra 1, primarily because that leading coefficient's equal to 1. Let's take a look at another problem. Exercise number 3. Solve the system of equations shown below using a graph on your calculator. Round all values to the nearest hundredth. Sketch a graph that justifies your answers. Now, I probably should have not even said sketch a graph, okay? But this is a system that, although you could solve it algebraically, especially once we had the quadratic formula, it would be rather ugly. So I want you to just do this one graphically, and notice it says round all values to the nearest hundredth, which implies immediately that we're not going to have really nice integer values, all right? So pause the video now, put these into your graphing calculator, and see if you can solve that system. All right, well, let's do it. Now, what I like about this problem is it requires you to play around a little bit with your graphing window. So let's kind of go through that procedure. I'm going to bail on this. Come on, there we go. I'm going to go into my graphing calculator. I think I'm just going to open up a new document. No, I'm going to add myself a graph. And let's take a look, right? My first equation is negative 0.5x squared plus 5x plus 7. Excellent. And my second equation is 0.75x plus 10. All right. And when you look at that, you can definitely see our linear curve. You can see our parabola there. All right. We know that the parabola is going to be opening downward because it's got a negative leading coefficient. So somewhere the intersection points are somewhere up here, right? And what we now need to do is we need to play with this window enough so that we see whether or not it's got intersections at all, because the line could actually just completely miss the parabola, or if it does have intersection points, where they are. So let's open up our window a little bit now. And there's a lot of different ways to do that. We could zoom out. We could do a variety of different things. In fact, I kind of like zooming out. It says center. So I just kind of click on the screen, and what happens is that the entire calculator just kind of zooms out. Now, one of the nice things about what I just did there is I can now see those two intersection points, one there and one there. I do kind of want to get the top of the parabola in there, and I probably have a lot more space here than I need. So now this is where I might go into my window itself and actually just play around with the settings. So to me, I feel, oh my goodness, didn't need it to go that fast. I'm going to go negative 10, and maybe that's a lot bigger than I need, negative 15. Now what I do want is a little bit more space on the upper side, so maybe I'll put 25 there, and just to make these numbers nice, I'll put negative 10 there. I like nice numbers. Let me just move that equation over here so that, oh no, if only there was an undo. It's still doing zoom out. That is so weird. Maybe please, let me just look real quick. Is there a zoom previous?
Zoom in?
Well, there is zoom in, definitely. It's unfortunate because I was hoping that we'd have a zoom previous, but we don't. Anyway, yeah, it's just not going to do it. Let's now find the intersection points. Okay, so we could play around and try to get the optimal window. I love zoom box. That's another nice one because you can draw a box around the window. And I had it well, and then I touched the screen and boom, it zoomed out on me again, which is unfortunate. But what we want to now do is we want to use that analyze graph just like we did before. We want to find our intersection points. So we're going to do our lower bound, do something like that. Go over like this. I hope it doesn't zoom out again on me. I mean, how long was it going to do that? Just carry that setting forever? Anyway, analyze graph intersection. We're already to the left of it, so I'll hit enter, move it to the right, enter, OTI. And there we go. So we've got our two intersection points, right? It says round to the nearest hundredth, so we can round those appropriately to the nearest hundredth. And now I think I'll draw a graph for you, but I'll use the window that I have sort of on my sheet. Let's do it. Not that there was anything particularly wrong about that window, but the idea is, you know, when you're solving something graphically, you want to put in a window that shows the important parts of the graph. So for me, that went from -5 to 5 along the x-axis, or -5 to 10 along the x-axis, and -10 to 20 along the y-axis. I don't have to make my curve sketches perfect, all right? Here's my parabola, and I'll call that y equals -0.5 x squared plus 5x plus 7. Label, label, label. We'll then have the linear curve kind of going like that, and that's y equals 0.75x plus 10. We want to label our intersection points. That's going to be 0.78, comma 10.58. And this particular intersection point is going to be at 7.72, comma 15.79. And those are really our answers, right? So our final answers, 0.78, comma 10.58, and 7.72, comma 15.79. So that was actually supposed to be sort of an experiment in you playing around finding a best window, and it became an experiment in me apparently not knowing how to use my TI calculator. Anyhow, there's our graph with our window marked, our two equations labeled, a really poorly drawn parabola, and two intersection points. I'm glad that they're not grading me on my artistic ability. Actually, they're not grading me at all. Now let's talk about a line and a circle. We can also solve systems of equations that involve a circle and a line. But let's remember something from geometry. Let's talk about equations of circles. A circle with a radius of r and a center at xc, yc has an equation given by x minus xc squared plus y minus y sub c squared equals r squared. So you should have worked with this equation of a circle extensively in geometry. For those of you that didn't take geometry yet but went from Algebra 1 to Algebra 2, I apologize, it sort of is what it is. All right, so let's take a look at exercise number 4. Given the system shown below, answer the following questions. X squared plus y squared equals 25, and y equals x plus 1. Letter A, identify the center and radius of the circle and plot it on the grid. All right, awesome. Well, here's our circle, right? Now, if we compare it to this form, we don't see anything being subtracted from either the x or the y, which means that the center of this circle is at the point 0, 0. It is the origin, which is nice. We like circles that have centers at the origin. Now, the number that's sitting over here is always the square of the radius, always the square of the radius. So the radius then will be the square root of that number, and in fact, then the radius is equal to 5. Now, ideally, the way that you want to graph this circle is what I would do is kind of put the center down and then go 5 units to the north of it, 5 units to the south, 5 units to the left, 5 units to the right. And then if you really want to be accurate, you want to make sure that you're nailing down your intersection points, you really have to have a compass, right, that you use to draw that circle beautifully. If you don't do it that way, then what can happen is you can find really weird looking intersection points. You know, there, of course, I've drawn it absolutely perfect. Now let's take a look at B. Solve the system graphically by also plotting the line. All right, so you've got to graph this line. I'm hoping you can do it at this point. Pause the video now and graph the line on that grid. Okay, well, keep in mind, to graph this line without doing anything fancy, even on our graphing calculators, what I would want to do is say, well, I've got a y-intercept of 1, I've got a slope of 1, so I could plot that y-intercept of 1 and then go up 1 to the right 1, up 1 to the right 1, etc. And I'm going to get a line that looks something like that. I'm like, where's my line? I don't know. And keep in mind, right, we're looking for those intersection points. We've got the two intersection points, one there, and it looks like the one up there in the first quadrant is at the point 3, 4, And the one down there in the third quadrant is at -4, -3. So that is the graphical solution to my system, right? And it's we're doing this kind of in the opposite order that we did exercise 1 in. We first solved it graphically. Now let's take a look at the algebraic way of solving it. Letter C. Solve the system algebraically by substitution. Now, when we have two functions, and a circle's not a function, when we have two functions and we want to find their intersections algebraically, we set the two functions equal to each other, all right? Because they're both y equals and y equals. Here, of course, we have a y equals, and that's a function, but then we have x squared plus y squared equals 25, and that's not a function. So in order to solve this one, instead of setting the equations equal, I need to take x plus 1 and I need to substitute it in for that y variable. So I'm going to have, x squared plus x plus 1 squared is equal to 25. All right. Now, in order to finish solving this, the first thing I really need to do is do what's called expanding x plus 1 squared. And maybe I do that somewhere over on the side of my paper. So, right, if you're not sure what that is, you just come over to the side of your paper, you do a little foiling, right, and you end up getting x squared plus 2x plus 1. All right, and that is just what x plus 1 squared is. That's all it is, right? That's just this. So I'm going to replace x plus 1 squared, don't want to lose that one, with x squared plus 2x plus 1 is equal to 25. I can combine these x squareds, so I'll get 2x squared plus 2x plus 1 is equal to 25. And now I'm kind of ready to start thinking about zero product law, factoring, and whatnot. So pause the video now and see if you can bring this one to its conclusion. Take a little bit of time to do that. All right, well, the first thing I'd like to do is I'd like to get the equation equal to 0. So I'm going to subtract a 25 from both sides, and I'm going to get 2x squared plus 2x minus 24 is equal to 0. Now we look at this equation and we think, well, that's a trinomial and its leading coefficient isn't 1, so maybe I go with the AC method of factoring. And you can totally do that. That will work and it's no problem. But if you're not particularly fond of that method of factoring, you can also note that 2, and 24 are all divisible by the number 2. So if you want to, I guess, make your life a little bit easier, you could divide both sides of this equation by 2, giving you x squared plus x minus 12 is equal to 0. And then you can solve this algebraically equivalent equation. That one's going to be pretty easy to solve, right? What I want two numbers that have a sum equal to 1 and a product equal to negative 12. Those two numbers are 3 and 4, with the 3 being negative, maybe not that negative, the 3 being negative and the 4 being positive. So that means all of this is going to factor into x minus 3 times x plus 4 is equal to 0. X minus 3 is equal to 0. X plus 4 is equal to 0. X is equal to 3 and x is equal to negative 4. Those are our x coordinates. Now to get your y coordinates here, I claim you really only have one choice. You've got to put them in the line. You've got to put them in this equation. Don't put them in this equation. That's actually going to give you too many answers, all right? But if we put them into y equals x plus 1, and let me just write that equation down here, the equation of the line, then I'll have y equals 3 plus 1 and y equals 4, giving me the intersection point 3, 4. And here I'll have y equals negative 4 plus 1. I love the fact that I wrote the equation down and then it vanished. And y equals negative 3. So we've got the point negative 4, negative 3. Awesome. There it is. And keep in mind, those are exactly the same intersection points that we found graphically. I find something amazingly satisfying about solving a problem in one method, right? Here we're doing it graphically, and then solving it in a completely different way, algebraically, and getting the same answer. But That's me. I'm a geek. You know, I love it. All right, more circle practice. When circles are not centered at the origin, the algebra can become fairly complex and lengthy. Trust that you have all the tools needed to solve these problems. So let's take a look at one of these in exercise number 5. Solve the system shown below algebraically. Show all work that leads to your answer. If you have a calculator that can graph circles, check to see if your answers are correct. All right, not all calculators can graph equations that kind of look like this, but some of them can, including our TI-Nspire, and maybe we'll take a look at that in a second. What I'd like you to do is pause the video now and see if you can work your way through this problem. And it may take you a little bit. You know, even accomplished students will probably take somewhere between 5 and 10 minutes to do this problem. So pause the video now and see where you can get. All right, well, just like the previous exercise, what I'm going to do is I'm going to start by taking 3x plus 10 and substituting it in for y. That's going to give me x plus 2 squared plus 3x plus 10 minus 4 squared is equal to 40. Now, before I do anything else, I think I'm going to clean up that second set of parentheses, right? 3x plus 10 minus 4 will be 3x plus 6 squared is equal to 40. That red's going to come out wherever it wants to right now. Now, I need to expand both x plus 2 squared and 3x plus 6 squared. I've got to like manipulate those and figure out what they are. I'll just do that like right over here. Right? So maybe over here I do x plus 2 times x plus 2. I do a little foiling, and that's x squared plus 2x plus 2x plus 4, and that gives me x squared plus 4x plus 4. So that's going to be what this one is, x squared plus 4x plus 4. And then I also need to figure out what 3x plus 6 squared is. So I put that on the side of my paper and I get 9x squared. This one's a little bit worse, plus 18x plus 18x plus 36, right? And that gives me 9x squared plus 36x plus 36. Yes, the numbers are starting to get a little bit bigger. So I get 9x squared plus 36x plus 36 is all equal to 40. Wow. All right. So now I want to collect like terms on the left-hand side of the equation. I have an x squared and a 9x squared, which gives me a 10x squared. I have a 4x and a 36x, which gives me 40x. I've got a 4 and a 36, which gives me a 40. And then that's equal to 40. Now at this point, I am ready to like start using zero product law. I need to subtract a 40 from both sides. That's going to leave me with 10x squared plus 40x. 40 minus 40 goes away, and that's equal to 0. And that's great. I really actually love it because, man, I don't know about anybody else. I was actually getting worried when I had this like 9x squared and 36x and all of that. But this is actually a wonderful equation to factor because it's just a GCF factoring. It's very similar to exercise number 1 if you go back and look at it. Right, at this point, what I can now do is I can factor a 10x out of both of those, and I'm left with 10x times x plus 4 is equal to 0. I can set my 10x equal to 0. I can set my x plus 4 equal to 0. This one I'll divide both sides by 10. 0 divided by 10 is 0. This one I'll subtract 4 from both sides, and I'll get x equals negative 4. So I now know the two x values where my circle and my line intersect. And now, way up here, I'm going to use this equation, y equals 3x plus 10, to figure out my y values. So I'll go down here. Let me just write y equals 3x plus 10, just so that you have it. So y will be 3 times 0 plus 10. So y will be equal to 10. And over here, we'll have y is equal to 3 times negative 4 plus 10. That's negative 12 plus 10, which is negative 2. And so my two intersection points, I'll put them right here, are 0, 10 and negative 4, negative 2. There they are. And remember what I said, right? Have faith that you have all the tools you need to get through the problem. Yeah, the problem might be long, right? It might involve quite a bit, but think about how many times you've multiplied two binomials together, right? You've done this again and again and again. That's probably the hardest, messiest part of the problem, right? That gets us all of this. You've definitely combined like terms a million times. So that's all we did to go from here to here. You've gotten equations set equal to 0 before. Factor, set equal to 0, back substitute, and we have it. Let's take a real quick look at how this can now be verified graphically on the TI-Nspire. Now again, this is a little tricky because not all calculators allow you to do this. I'm going to open up a brand new document. I'm going to add a graph. Now, what's interesting about this is that when you initially try to graph something in the TI-Nspire, all you have here is f1 of x equals, right? That means that it's looking for a function. Now, of my two curves, one of them is a function, and that's my linear one, all right? So I could, right now, just put that one in. So I'm going to put in 3x plus 10 as f1, right? And there's that. But how do I get the equation of the circle in? Well, if I hit Menu and I go to Graph Entry Edit, right, the first one says function, but the second one says a relation, all right? And notice how it says relation 1 x comma y. It literally is saying to you, you can now put anything in, and I could even put a function in right now. I could say y equals, 3x plus 10 or whatever it is. But I can actually put in the equation of my circle now. I can put in x plus 2 squared plus y minus 4 squared equals 40. And then it's going to graph my circle. Now, it doesn't get my circle entirely in there, and I'm almost scared to do any zooming right now, but I'm going to do it anyway, and I'm going to zoom out, and I'm going to get my circle center. It still thinks I want to zoom out. I don't know why. Anyway, what's cool is now we can use the intersection. One of the weird things about it is that it works a little bit differently. Notice here now it says first corner, right? It's asking you to basically put a box around where you think the intersection point is. So I'm going to put enter. Second corner, notice how it starts to draw a box. And I put enter, and there's my intersection point. Likewise, I can do it for the other one. Analyze graph, intersection point, first corner, enter, drag that box around, enter, and there's my second intersection point at 0, 10. Really super duper cool. The fact that you can graph both a circle and a line in the TI-Nspire, and it will even find the intersection points for you. All right, great way to verify that we have the right answers. Let's go back and let's wrap this lesson up. So the idea of systems is an exceptionally important one in math. The idea that you can have 2 or more equations in 2 or more variables. When you solve a system, right, algebraically, what you're doing is you're finding the intersection points of those 2 relationships. Whether they're both functions or one of them's a function and one of them's a circle or a non-functional relationship, doesn't really matter. Most of the time what we do is we substitute or set 2 equations equal to each other, and at least in this unit, almost always we then use the product law to sort of solve our equations to find the intersection points. All right, solving systems of equations is going to come up repeatedly in this course, so we'll see it a little bit more. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.